The Steady Thermal Aero Research Turbine Lab was started with the purpose of improving gas turbine engines, particularly to reduce fuel burn.
Additive manufacturing, or 3D printing with metal, is a big research area at START. We're looking at how designers can leverage AM to make more effective cooling schemes for gas turbines.
So the parts that we're testing are made with a laser powder bed fusion process, where a laser beam is used to melt metal powder layer by layer to create a three-dimensional part.
We're trying to understand how the roughness affects the aerothermal performance of our cooling panels.
So we've designed these coupons and a test rig that allow us to evaluate microchannel cooling designs so that we can determine how they perform in terms of heat transfer and pressure loss at engine-relevant conditions. Traditional or a non-optimized channel design that's very simple can actually perform similarly to a highly engineered design produced using traditional manufacturing.
One of the areas we're studying with the turbine rig is rim seals. One of the challenges of gas turbines is that you have rotating components going past stationary components, so you need to prevent hot gases from leaking through the rim seal gap. What's done is force cold air into the cavity region to stop hot gases from making its way into the cavity. Using too much air lowers the efficiency of the engine, whereas not using enough causes hot gases to be ingested into the cavity region, damaging engine components. My role is to study the physics of what's going on in the cavity and improve our understanding of it, so we can design more efficient engines in the future.
We're also using the turbine rig to study turbine blade heat transfer. Jet engines have air temperatures that are hundreds of degrees hotter than the melting point of the metal in the blades, so they need to be cooled to survive the extreme conditions. I'm working on using thermal imaging to measure temperature and heat flux over the surface of a turbine blade while it's spinning at about 10,000 RPM.
Penn State has a lot of resources that are valuable to grad students and researchers here. So my research focused on developing a heat flux gauge for turbine applications. These gauges are really small, about 250 microns across, which is roughly a little bit smaller than the size of a normal grain of salt. But one of the cool things about creating something so small here at Penn State is that we already have the nanofabrication infrastructure on campus. I can actually design and manufacture them myself, which wouldn't be possible at a lot of other institutions.
Since our research is so focused on studying gas turbine technology, collaboration with industry plays a big role in START. It's a unique and valuable experience as a graduate student working so closely with industry. I really like knowing that my work is having a real-world impact.
As a first-year graduate student, I've really been welcomed into the group. With all the different and complex projects going on here at START, it was a little overwhelming at first, but I can honestly say that between some of the older graduate students and the full-time staff, there's always been somebody there to help show me the ropes.
The success of START is really driven by the graduate students. Our students publish papers, and each year we go to ASME's Turbo Expo where we present our work in front of an international audience. My students go on to become professors, senior engineers. They are very successful working in industry and project managers in government agencies.